begin with a word of prayer. So, Heavenly Father, we thank you for this day. And Lord, I thank you for these students and this opportunity we have just to meet together and study your creation. And I just pray you'd just guide our thoughts today, Lord. In your name I pray. Amen. All right, so we have begun our discussion. So remind me to collect your homework at like the end of today, right? It's due today, right? Yeah. So we have begun our discussion, of course, of Galois theory. And so we got to the point of defining the, sort of in the start of section 14.1, of course, we have thus far defined the concept of a subfield fixing automorphism of an extension. I mean, if you have an extension field over some base field, then we can look at the automorphisms of the extension field which fix the base field, let's say. We can look at the collection of all those aught k over f automorphisms. We proved that those form a subgroup. We proved that any of those subfield fixing automorphisms move roots to roots if there's a root. We proved that also we could reverse the correspondence and find a collection of elements of a given field which fix the elements in a given subgroup of the automorphism group. I think at this point it would be helpful to introduce some language from a different thing. So this is the Galois correspondence, which is a blurb by Keith Conrad. So Professor Conrad is very generously provided a bunch of PDFs on topics ranging quite a spectrum of things, but he's got probably about 4 or 5 little PDFs specifically targeted to Galois theory. And he is aware of Dummett and Foote. In some sense, these PDFs parallel, supplement Dummett and Foote actually pretty nicely. And so he also has some notation which I don't think is in Dummett and Foote, at least I haven't seen it yet. And I think it's helpful. So let me just kind of run through his introductory discussion of this. And I think it'll help reinforce what we did last time. All right, so this is, in particular, the Galois correspondence. All right. So he's studying, L over K extension, field extension, right? Just like we can look at sigma that goes from L to L, such that what? Sigma of K is equal to K for all K and K, then we'd say that sigma is an element of what? Aught what? Right, it's a automorphism of L which fixes K, so it's in aught L over K, right, very good. Now, it gives an example that we haven't studied yet. I mean, maybe we've studied it. I think you've studied this since high school, probably. But his example, which is nice, is we can look at sigma from the complex numbers to the complex numbers, where we define sigma z equal to z conjugate, right? This is a pencil up here. Exciting. Now, so that's an automorphism of C, obviously, right? Right, that's clear enough because, you know the deal, sigma z1, z2 with z1, z2 conjugate, which is, of course, the product of the conjugates, right? And it also plays nice with addition, subtraction, maps 1 to 1, all that fun stuff. It's definitely automorphism because it is its own inverse, right? Also, sigma inverse is just given by conjugation because the conjugate to conjugate's back where you start. And it's also not hard to see that if we take sigma of x plus I times 0, right, we get x minus I times 0, also known as x, right? So it's pretty clear that sigma is in fact a what? It fixes the real subfield of the complexes, right? In other words, it's an R automorphism, all right, in the natural sense. All right, so proposition 3, all right, this basically what I'm about to give is proposition 3 last time justified the definition. Proposition 3 from last class, prop 3 of section 14.1, can't do 14.1 in Dumb and Foot, justifies the following definition. And I think this notation is helpful. This notation, I think, is very helpful. Definition. So for any subgroup, all right, H of ought, L over K. So here again, I'm assuming what? L over K extension, right, of fields, all right? So if you have any subgroup of the K-fixing automorphisms of L, right, then we define a field, and here's the field, L, H, L upper H. And L upper H is the fixed field of H. In particular, this is alpha in L such that what? Again, it's the fixed field of H. So what does that mean? H is a subgroup of automorphisms, so it means what? H of alpha is equal to alpha for what? For all, oh, yeah, little h, thank you. You fixed it for me. Very good. Little h of alpha is equal to alpha for a little h in big H. Probably a bad form to use big H as the variable in the name of the set. Yeah. So this is the fixed field of H. All right. So, all right. And so basically we explained last time that that is in fact a field. Right. All right. In fact, it's a subfield. All right. So here's the basically we're studying so. Two correspondences. In particular, we're studying, F, ought, L over F, right? So the subgroup corresponding to a given intermediate field, right? But also, what's the other? H, the fixed field of H. Right? So we're studying two correspondence, for a given, L over K, I suppose. Now, so how's this work? A picture of this let's see here. So we have K up here, right? Because that's the extension, and we have. Oh, I'm sorry. I'll get it straight eventually. L, rather, right? That's the sort of the biggest field in question here at the moment. The intermediate field is what? Well, I guess I'm just here. I'm going to follow Conrad's blurb here for a second. So if we have L and we have two intermediate fields, say F prime and F prime prime, and then that is of course over K, right? So you have this tower of fields. Then it turns out that we can prove that correspondingly there is at the top the identity group, and then what goes below that. The automorphisms of L fixing what? And then the automorphisms of L fixing what? And then the automorphisms of, let's see here. So down here you have the L over K, and this is actually, I think F prime prime here and F prime here. Oh, I'm sorry. He doesn't have a prime prime. Let me unprime prime things. He just makes it F. I'm an idiot. There we go. So let's see here. This is actually the picture that corresponds to the next result in Dummett and Foote that we have not yet written down, which I will now write down carefully to try to make sure we understand. So let me just read here. So the correspondence F corresponds to the F fixing automorphisms of L, and the correspondence H corresponds to the fixed field L of H between intermediate fields, and the extension and subgroups is, he says, is inclusion reversing. All right, so here's the little theorem, if you will. Here's the more stated in terms of sets. So if F is a subset of F prime, all right, then ought of L over F prime is a subset of ought L over F. So that's one thing. And then two is that if H is a subset of H prime, then the fixed field of H prime is a subset of the fixed field of H. These are the inclusion reversing aspects of these correspondences. Okay, so let's just prove these. I mean, it won't take but a minute to prove these, I think. How would we prove this? I mean, so of course, this is all happening what? These are assumed to be what? Intermediate fields for some extension, right? So we have, the backdrop here is we have base field what? K, and we're looking at F being a subfield of L, right? Well, in F prime, I mean, it could be that these right here are in fact equalities. They're not, genuine extensions or anything. They're not proper extensions, but that's the idea here. Okay, so assuming F is a subfield of F prime, how would we show 1? I guess we should probably pick sigma in the F prime fixing automorphisms of L over F prime, right? I mean, understanding the result is much harder than proving the result in this case. Right? It's not always that way in here, but in this particular case, check it out. So let X be in F, right? What happens then? X is in F prime, right? So sigma of X is equal to X. Because if it fixes F prime, it certainly fixes any subset of F prime, which is to say that sigma is a F fixing automorphism of L. So therefore, thus, sigma is in aught L over F, right? And that proves 1. I don't think I'm exaggerating. I think this is harder to understand than to prove, right? Yeah. Proof of 2. So suppose H is a subset of H prime, right? And we would like to suppose alpha is an element of L of H prime, right? What does it take to show that alpha is in the fixed field of H? We should let little h, I learned my lesson, be an element of H, right? Which is, by the way, a subset of H prime. So therefore, H, little h, is an element of H prime. Hence what? H prime, by the way, is a subset of what? Aught K, by the way. Right, this is all happening under the auspices of some extension, the fields, K being the overarching one. And so then what? H of alpha is equal to alpha, right? Which implies, of course, that alpha is in the fixed field of H, since I just showed that it was fixed by an arbitrary element of that subgroup of automorphisms, namely H. Okay. I think, so Conrad says that this is nearly a tautology, this correspondence, right? All right. Some other things you could say, right? By the way, we could write this L of aught, L over K equals to what? If you guys understand, you ought to be able to fill in the blank for me. Actually, this is not guaranteed. What's one possibility, but it's not the only possibility. contains the field L. Well, this is this is contained in the field L. That much is for sure true. This is a subfield of L. Right. If this was equal to K, he says this is desirable. But that doesn't always happen. Here's his example of that. And we actually looked at this example last time, although not from this perspective. If we look at Q adjoin the cube root of 2 over Q, right? This has what? So what's the degree of this extension? So what's that say about intermediate fields? There are no proper intermediate fields, yeah. And in fact, we argued last time. What did we find? We found that the group ought Q adjoin the cube root of 2 over Q was what? Is a trivial group, right? There's only one automorphism. It was the one that fixed everything. Because we can only send the cube root of 2 to the cube root of 2. The other two roots being permuted by such automorphisms, All right. They were not available in this extension field, so we only had the identity automorphism. Let's see here. So in this case, let's see here. I think the equality would not be met here, would it? Like what would Q do cube root of 2 ought Is this equal to Q? Right. So that's not K, that's actually L. Let me put this into words for you. So this is too big since this is too small. The next example Conrad gives involves separability, so I'll skip that. Anyway, I just encourage you to read. Study Demet and Foote to start with, but then once you've sort of done your first pass through that, if you want to understand things more deeply in the fastest way possible, reading this is helpful. It really will help you round things out, which is why I'm spending some class time on it also. All right, so at this point we reach the next section in his correspondence PDF, and this also contains a useful definition. The roots of a common irreducible polynomial in K over X are, let me just use a little x there. I usually use a little x. Kx are called, that was supposed to be called, K conjugates. All right. They're called K conjugates. So, for example, if we look at q adjoin the square root of 2, right, then we have what? X squared minus 2 in q of x, right? So plus or minus root 2 are q conjugates. Right? Another example of this would be if we look at, R adjoin I, also known as complex numbers, and that's tied to the polynomial x squared plus 1 with real coefficients, right? Then plus or minus I are complex conjugates. Right, so the notation is in agreement. Don't agree with me, that's nonsense. I'm testing you. Are you paying attention? It's a trap. Oh, the same. Irreducible, yeah. It is, it's the common use of common, yeah. No, this should definitely be R, which is unfortunate that the standard usage of complex conjugate is at odds with this more refined notion of conjugation born of Galois theory. Yeah, those are R conjugates. Because the polynomial to which they both are found zeros of has its coefficients taken from R. This is nice language, though, because this means we can restate the main theorem from last time in terms of conjugates, right? We proved that. What did we prove last time? We proved basically that if you had f of x in f of x, and k is an extension over f with alpha in k such that f of alpha equals to 0, then f of sigma alpha equal to 0 for all sigma in what? For all sigma in the f-fixing automorphisms of k, right? I mean, this was a joyful thing to prove last time, really simple. Just straightforward application of the definitions and everything. But we can recast that statement now in terms of, well, f conjugates. What this says is that, what does it say? I mean, alpha and sigma alpha are f conjugates. So, what does this actually say? So I mean, we put that in words. So again, because this proposition from last time says that, alpha and sigma of alpha are f conjugates, right? Conjugates. Thus, what? Automorphisms, affixing automorphisms over k, do what? Permute, right? Roots of f of x. So we can naturally view the f-fixing automorphisms of k as being permutations on the roots of given polynomials with coefficients in the field f. All right. And again, Professor Conrad has nice examples to follow this, which I will not go over because our time is limited. So his next section, which is nice. I mean, he's got multiple sections which are basically unwrapping section 14.1 in Dumb and Foot. Right? It's a further breakdown of the ideas. I find it useful. Also, his proof of the central theorem is 2 pages compared to Demonfoot's 1 page. So, yeah, there's that. Theorem 3.1, and it's not because he's a dummy, it's because he gives a more nuanced, probably more general argument. Anyway, not to digress. For any finite extension, L over K, the group ought L over K is finite. So I buried the lead here. The goal of this section is to show that ought, basically to bound the size of ought L over K. All right. So, all right, this is the first step in that direction. What's the proof here? If it's a finite extension, what can we say L is equal to? All right, so K adjoins some algebraic elements, say alpha 1, alpha 2, alpha n, whatever, right? And then he points out that any automorphism, right, in K over L is determined by what? It's fixed by its action on what? You know, let's say by values. By what values? By sigma of alpha 1, sigma of alpha 2, right? Sigma of alpha n. Wait a minute, what about what about K? Well, remember, we're looking at a, hey. Oh, this, of course, whose fault is this? Whose fault is this? Is this Conrad or is this me? You know the answer to this already. It's me. Let's see here, so. All right, sorry, yes. K is fixed. I mean, that's not up for grabs. So we really, once you say where the generators alpha 1 through alpha n go, that uniquely defines the automorphism, right? Right? So, and he says each sigma of alpha I is restricted to lie among the finitely many K conjugates of alpha I in L. So each element of ought L over K is determined by a finite amount of information, which makes the group ought L over K finite. So, I mean, these don't, I suppose, you mean, my sort of sloppy thinking at the start, which is wrong, is that, oh, well, you have to send this to 1 of alpha 2 through alpha n or itself. That's not right. The point is, there are polynomials, right? There exists something we have not written. There's like f1, there's an f2, there's fn, polynomials, which take those as zeros because they're algebraic elements. And those polynomials have a certain degree. By the theorem we just talked about, you have to send, under such an automorphism, you have to send that 0 to another one of the zeros. It's a permutation on the zeros of f1, the zeros of f2, the zeros of fn. But there are, in principle, n polynomials to think about, each with its own set of however many zeros to permute about. So the counting is not as simple as just n factorial. It's more than that. It depends on the degrees of the elements and so forth. Exactly. This doesn't have to be a splitting field for I suppose if you take the product of all of them, it's probably a splitting field for that, but whatever.
No, it wouldn't be, right? Because, like, for instance, if you have a degree like 7 irreducible polynomial and you have an extension over one of the roots.
Let me say it another way. It contains a splitting field for them.
Would it? Like, what about?
Oh, would it? Yes,
Like
that
polynomials
you're
are
right.
going to adjoin multiple.
You're right. We don't know that it contains a splitting field just yet. I mean, it certainly touches on a splitting field. It's got something in common with them, right? Because they're at least giving us one zero, but there's no guarantee that all the zeros have to be in there. Like the too big, too small example we talked about already today. You're right. In fact, that is the quintessential issue. All right. So the big theorem here, which is his theorem 3.4, and I'll tell you which number it is in Dumb Foot in just a second here. So I'm using Conrad numbering. Again, it's the Galois correspondence. It's important that I tell you which one because he's got about 4 of them. This one's 27 pages long in its current form. All right, anyway, so here it is. Let sigma k to k prime, isomorphism of fields, and he has f of x in, he actually uses a big X here, but I'm going to use a little x at the risk of ruining some other system of notation. Anyway, so f of x and k of x. He says L a splitting field of f of x over what? Over k. And let's see here, L prime, a splitting field for what? Sigma of f of x over k prime, right? Over k prime, all right? Then the degree of L over k is equal to the degree of L prime over k prime, and also sigma extends to isomorphism of L to L prime. And more than that, the number of such extensions is at most L over k, the degree of L over k. We have this little picture, L, here's the given data, L is an extension over k, there's an isomorphism sigma to k prime, L prime is the extension of k prime. What theorem 3.4 is doing for us is extending sigma up to here. That's the extension of sigma. Although he does not, I mean, well, I don't even have a name for it actually. It's the extension of sigma, all right? You could call it gamma, such that gamma restricted to k equals to sigma if you like. What's new here? What's the new here thing? I think we had this theorem before, right? I feel like this is in chapter 13 of Dumb Foot, in fact. But what's new? What was not present before is this little bit, this little thing right here. The number of such extensions is at most L over K. That's new.
Because each extension is determined by a permutation of the ratio of x.
Yeah. Now he says we should skip the proof in a first reading, so I'm not one to ignore sage advice. Yeah. So there's a corollary to this, though, which I should write down. I probably will soon regret erasing what I just erased.
So we can't say it's at most the degree of f of x because it's not like splitting fields can have degrees.
I think we're very much involved in some of the same counting. We'll all get it out on the table here before too long. So corollary 3.6 is that if L is splitting field, over K of f of x and kx, right? Then the number of k-fixing automorphisms of L is less than or equal to L over K. The proof, simply apply theorem 3.4, right, with k prime equals to k and L prime equals to L. And what do you want for your isomorphism? Right. All right, so then if we add the separability assumption, then we'll get a stronger conclusion. In fact, the bound in theorem 3.4 is reached. So theorem 3.7 says if we have sigma going from k to k prime, an isomorphism of fields, and f of x in kx with splitting field L, all right, over K, and L prime splitting sigma of f of x in k prime of x over k prime. I feel like I'm writing, I need like a big old rubber stamp to just write these two sentences. I should have given these sentences a name and just written that again. Pac-Man or something. If, finally, f of x is separable, what's that mean? No multiple roots, right. If f of x is separable, then there are L over K extensions of sigma to an isomorphism all right, that proof actually doesn't look too bad, but we don't have time today. And corollary 3.8. Corollary 3.8 says that if L over K is splitting field, right, for f of x in K of x, right, over K, then what? The number of K fixing automorphisms of L is what? Right. You got it. As to not bury the punchline here. So let's see here. This one is proposition 5 in section 14.1, Dummett and Foote, right? And this, what we're discovering right here, in Dummett and Foote, leads us to the definition that if we have K over F as a finite extension, then K is said to be Galois over F, and K over F is a Galois extension if this is met. Such an extension is said to be a Galois extension. So in particular, well, not assuming the separability, but I mean, this right here is what's required for L to be Galois over K. So that definition is given on page 562 of Dummett and Foote. And in that case, the automorphism, F fixing automorphisms of K are called the Galois group of K over F. So the Galois group, for example, of x squared plus 1 would be what? The identity, I mean, it's the identity in complex conjugation would form the Galois group for this polynomial. But anyway, obviously, the next stage in the game is to talk about how to attach a group to a polynomial and just to clarify these ideas and continue on. I'm sorry it takes a long time to get everything out on the table here, but I think it's important not to rush. So I think I've achieved that goal. You guys have a good weekend? Yeah.
I wish I started working this earlier.
Ah.
I finished all before.
Oh, but you finished the last 10.